In this video, we're going to look at linear approximations. So we see from the prompt that's one of the first words in the problem, right? We're going to find the linear approximation L of x to the function y equals f of x near x equals a. And so then we have some specifications on what those different values are. So what we're doing is this L of x here, what we're actually going to be finding is a function. We're not going to be looking for a specific value, we're going to be looking for a function that allows us to approximate values of this original function near this a value here. So that's how this problem's kind of laid out for us. And now we want to talk about how to find this L of x. So in general, for a differentiable f of x, which this is, 1 over x plus 4 can be differentiated very easily. When we have a differentiable f of x, the equation of a tangent line to that function at x equals a can be used to approximate f of x for x near a. Hence why it's a linear approximation. We're using the equation of the tangent line to approximate values of our original function, and the tangent line is typically a linear function, so that's why it's called linear approximations. So what we're going to do is we're going to start with the equation of a tangent line of f at a to see where our linear approximation equation comes from. Okay? So what I mean by that is normally when we talk about equations of tangent lines, we go from point-slope form to slope-intercept form, and that's going to kind of be what we're doing in this case as well to figure out what the parent form of our linear approximation equation rather, comes from. Okay, so we know normally we start with y minus y1 equals m times x minus x1. How we normally call y and x are f of x and x, right? This x is an independent variable and y is a dependent variable. So we're going to go ahead and make that substitution inside of this. And then now what we're going to ask ourselves is, since we're dealing with values near x equals a, this x1 and this y1 are going to reflect that change. So we're letting x1 equal a, and so similarly to how this x equals x and this equals f of x, y1 is going to represent f of a. So now we have f of x minus f of a equals something times x minus a. Okay? Now, what is this m? Normally when we're talking about in calculus, the slope of something is its derivative, right? But what we're going to actually end up doing is normally how, when we find this derivative, we would evaluate our function to find its derivative and then plug in the point that we were trying to find the equation of the tangent line at into our derivative function to figure out the slope at that point. We're going to do that same thing here, and so that's where this f prime of a comes from to represent our slope inside of this point slope form. So this is what we're dealing with so far, and now what we're going to actually end up doing is we're going to add f of a to both sides here. So we get f of x, this function, equals f prime of a times x minus a plus f of a. Okay? And like we said, since we're approximating this f of x, this original function, we're approximating the values, is going to become approximately. So f of x values is approximately equal to this that we have here, and this is actually where our linear approximation formula comes from. It's this whole thing right here. So our linear approximation formula follows a very similar pattern to something we've already seen before. I just kind of wanted to highlight where it comes from, how it's derived, and then how we use it. So we've come up with a way to figure out what the linear approximation function is, but now we've got to figure out what these different values are inside of here to come up with our actual linear approximation function. So in this case, the values that we need to be concerned with finding are not necessarily x. This x is going to be our, again, independent variable that we're going to change values of, because we want to find approximations of values of x that are near this -3. So we can plug in values near -3, and this is going to be where we're going to plug in those values. So the values that we need to find are f prime of a, and f of a. Well, these last two values here, this a is given to us in the question, right? We know that a equals -3, but then we can find f of a pretty quickly, right? We find f of a by plugging in f of -3 into f of x. So what we get is 1 over -3 plus 4, or 1 over -3 plus 4 evaluates to be 1. So we know that f of -3 is 1, a is -3, So the only real value that we still need to find is f prime of a. And how do we find that? But by taking the derivative of f of x and then plugging in -3 into that derivative. So let's come down here and evaluate what f prime of x is. So when we see f of x equals 1 over x plus 4, we're going to need to take the derivative of this thing. So now there are a couple ways we can go about this. We could use the chain rule, we could use the quotient rule. We've done a lot of the chain rule recently, so I'm actually going to do this by taking the quotient rule of this function here. So if we label this as f and this is g, we have f is 1, g is x plus 4, the derivative of g is 1, and then the derivative of f is 0. Okay? So then the formula, or the way that we remember the quotient rule rather, is low d high minus high d low all over the square of what's below, right? So low times d high is x plus 4 times 0, so that gives us nothing. So we have 0 minus high d low, 1 times 1 is 1, all over the square of what's below, right? So what this becomes is -1 over x plus 4 squared. Okay, so this is our derivative function here. So now, to find f prime of a, we need to evaluate f prime at x equals -3, and so this gives us -1 over -3 plus 4 squared. So we get -1 over, and we remember -3 plus 4 is just 1. 1 squared, -1 over 1 is just -1. So f prime of -3 is -1. We have all three of the values that we need to plug into our linear approximation function. So let's go ahead and figure out what our linear approximation is for this case of the things that we've been given. So we have L of x is going to equal f prime of a is -1. So we have -1 times x, remember it stays in variable form, minus -3, and then we get plus f of a, and we evaluate f of -3 to be 1. So we have this going on. Okay, so if you were to stop here, WebWork would totally accept this answer. I do believe I tried it a little bit earlier on and it took it, but it gives you a different answer to compare it to. Like, this is a similar way of expressing the answer, but I want to show you how WebWork got the answer that it got. Okay, so what they actually went through and did is they went through and distributed and simplified this stuff down a little bit. Okay, so if we distribute -1 in this parentheses, after taking care of the fact that if we subtract a negative we get plus, we get -1 times x and -1 times 3. So we have -x minus 3 plus 1. And if we combine like terms here of this -3 plus 1, we're going to get -x minus 2. And if we take one more step of factoring out that negative from both terms, we're going to get negative times x plus 2. And this will be more closely representative of the form of the linear approximation function that WebWork returns for this question. So what we did in this video was we went over how the linear approximation function, where it came from, and kind of how it looks and how it works closely with the equation of a tangent line and why it is the way that it is. But then we also went over the process of solving how to find a linear approximation function in this way. We're given two of the values pretty easily, but the third value that we need to find involves taking the derivative, which is why this topic was safe for calculus, because it involves taking the derivative and then evaluating that derivative at our point in question.